sure that things
See
here
this?
can be seen.
Yeah.
Or I think Sarah did a little scoochy. Okay, guys, today is your introduction to free body diagrams, which is intimidating at first until you get the hang of it. That's the easiest thing in the world. Newton's third law, objects feel each other. One of the problems about trying to account for all the different forces with arrows and signs is that those arrows get confusing. Who's feeling what? So in other words, if I drew a picture of the bench press, right, the one we did in class on Monday, back here, doing the bench press, and I say, hey, what does the bar feel? We establish that the hand's this way. What do the hands feel, the bar that way? If I'm actually drawing on the picture, well, wait, is that what the bar's feeling, or is that pulling on the, you see what I'm saying? When you draw both objects that feel each other, it gets very confusing on who feels what. So free body diagram is simply whatever object you want to analyze by itself. It's not saying the other objects aren't there. We're going to account for the forces from the other objects. We're just not going to draw the physical other objects because it's going to get confusing of who's feeling what. Okay? So I gave an example from our last class. If we're analyzing what the barbell feels, we're not going to literally draw the hands. We're going to represent the force from the hands on the bar. But if we actually draw on that picture on the left, that's going to be very confusing. Is there a force pulling on the hands? Is there, right? So it's not to say we are forgetting the hands. We're just representing the hands with their influence, and we are isolating the object that we want to analyze. For some of you, when you're analyzing people, if you're looking at all the different things influencing them, you're going to represent the force from the floor, but you just want to actually draw the floor because, again, that's going to get very confusing, okay? F is equal to ma. Forces influence movement. More specifically, I have some little cheat sheets up here, okay? For these analogies, up is going to be positive y and down is going to be negative y. Ups and downs. Cheat sheet here, F is equal to ma. True. It's directional dependent. This is a y conversation. So the sum of the forces in the y is going to influence motion in the y. All that means is that if I can't give a force to Miriam in the x and make her move in the y. Like if I want to lift that chair up and make it move up, I have to apply a force that's up. That's all that means. If I want to make the ball move across, I have to give it a force across. X forces influence X motion, Y forces influence Y motion. That's all that means, okay? If the sum of the forces is positive, that object has to have a positive acceleration. That's like saying plus 20 is equal to plus 20. Plus 20 can't equal negative 20. Remember when we did our equation equivalence. If the sum of the forces is negative, that means the acceleration has to be negative. Remember, we don't use deceleration. Here's the next point, and hopefully all this will make sense at the end of class. What does it mean to be positively accelerating in the y? Well, positive acceleration, because of a positive force acting on you, can do one of two things. It could either speed something up, going up, but it could also slow something down, coming down. I'll give you an example of that. The ball is falling down. When I slow it down, I gave it a positive acceleration because my hand was pushing on the ball more than the planet was pulling down on it. I had a positive unbalanced force. So the acceleration had to be positive. That's a little weird because, again, we like to think of, well, acceleration means to speed up. No. Acceleration just means change in velocity. And sometimes that means your velocity gets greater. Sometimes it means your velocity gets less. It's all forms of acceleration. Negative acceleration means either speeding up in the negative. I'll give you an example of that. I let the ball drop. It's getting faster and faster and faster and faster because the only force acting on it is in the negative direction. But negative acceleration can also mean slowing down while the object is moving in the positive. And that sounds like a lot, guys, but it's really not. If I toss the ball in the air, as soon as it leaves my hand, isn't it slowing down as it travels up? Isn't it getting slower and slower and slower as it's still moving up? That's a negative acceleration. It's slowing down as the velocity is traveling up. Now it's getting slower and slower and slower, but the sucker's still moving up. Yes? So here is hopefully the antithesis of today's lecture that we're going to graph out. I'm going to show you that when the ball leaves my hand, and this will apply to the bench press eventually, when the ball leaves my hand, it is negatively accelerating the entire time it's in the air. Both going up and coming down. Gravity is slowing it down as it's traveling up, changing its direction, and then speeding it up as it comes down. It's the same acceleration. Because the only thing influencing this ball when it's outside of my hand is planet Earth. So if the force is negative, the acceleration is going to be negative. Think of it like this. This is how I like to think of constant acceleration, though we have different velocities, directions of motion. I like to think of it as mile markers going into a new state. You're in Louisiana or Mississippi, and the mile marker from your end starts to get less and less and less. Like, oh, let's say we're going to -4, -3, I'm sorry, like 4, 3 miles to the border, 2 miles to the border, you're passing through 0, still moving in the same direction. This is an analogy, but then all of a sudden it's 1, 2, 3, 4, 5. You're slowing down as you go up, so your velocity is going +4, +3, +2, +1, 0, -1, -2, -3, -4, -5. But the only thing that can make that happen is a constant force in the same direction. In other words, if I didn't have that negative acceleration, the ball wouldn't slow down, it would just keep going. The same force that sped the ball up going down had to slow it down going up. Does that make sense? Okay. So here's my little picture. I mean, just one, right? I mean, that's Picasso. Okay. Toss the ball up, and the ball comes down. Now, I'm establishing, all we're looking at is the ball when it leaves my hand. Remember, for follow-through, once the ball leaves my hand, I can't do this, and the ball, like, wait, where do you want me to go? Once it leaves my hand, I can't influence it unless I'm a wizard. So the ball leaves my hand, it goes up, and it comes down, and I'm going to stop time right before it hits my hand. In other words, planet Earth's the only thing influencing the ball. What about air? Negligible if I'm just tossing it up in there. Does that make sense? If I'm throwing it as fast as I can, we could talk about air. But if I'm just doing this, no, not enough to put into the equation. Good morning. So let's look at some things. This is what we call a velocity time graph. In addition, I know we're talking about ups and downs, so I'm going to say, hey, the specific directional speed, velocity, of that ball, specifically in the y direction, as it goes up and down, which takes time. Everything takes time. Okay? The x-axis is going to be time. The y-axis is going to be velocity, but it looks a little weird. Maybe y'all never seen graphs. Y'all seen this graph? All I'm doing is adding a bottom because we're going to have positive velocity, we're going to have negative velocity, and we're going to have no velocity. Y'all are going to be astounded because this is a level of calculus, but it's going to work. It's coming. Remember how I said you guys know more about physics than you give yourself credit for? I'm about to show you. When the ball leaves my hand, I'm tossing it up in the air. When the ball leaves my hand, does it have velocity? Yes or no? When it leaves my hand, yeah, it's moving. What direction is the velocity? Positive or negative? Toss it up in the air, right when it leaves my hand. Positive. It's moving up, it's traveling up. True? So that means I can't be here when I start time. Remember, time's going to start right when it leaves my hand. I can't be here. I can't be at 0 because it's moving. And I can't be down here because this means it's moving down. I have to be up here somewhere. Where am I at? Who cares? I'm showing you trends. So this is 0 velocity. As I go up the y-axis, that means I'm getting faster and faster and faster and faster in the positive y. As I go down here, I'm getting faster and faster and faster and faster in the negative y. As I travel here, I'm getting slower and slower and slower and slower in the negative y. As I travel here, I'm getting slower and slower and slower and slower in the positive y. What if I'm passing through Mississippi? No problem. I'm getting slower and slower and slower and slower and slower and slower, past 0, faster and faster and faster and faster and faster and faster. So far, so bad. When I toss the ball in the air, it has positive velocity. But what's going to be happening to the movement? Will it speed up when it leaves my hand, or will it slow down when it leaves my hand? Yes. Guys, we're in layman's terms. I'm not trying to trick you. Heck yeah, it's going to slow down. I know it because we've done this experiment 1,000 times when we were kids. So that just means that it's going to get, when it leaves my hand, it's going to start to drift closer to 0. True? But if I draw a line straight down, that meant it happened in no time. Everything takes time. So the trend is going to be, as it's slowing down, as it slowed down, time elapsed. That's all that slope means. How much time? Who cares? How fast was it going? Who cares? I just know that when it's in the air, it's going to slow down until at the very tippy top, at the tippy top of whatever distance, there is going to be an instantaneous little moment where it's going to have 0 velocity. And you know why it has to have 0 velocity? How is it ever going to come back down to me unless it stops going up? Okay? Okay? So I'm going to call this point A, it leaves my hand. I'm going to call this point B, it's at the highest point in the air. So far, so bad. Now, I'm going to dig into your trigonometry and ask you guys, what is the direction of that slope from A to B? Is it a positive slope or is it a negative slope? Y'all know what slopes are? It's okay to say no. I'm from Delphine, Louisiana. The way I look at it is, it's rise over run. The way I look at it is, if I'm climbing up, that's positive, and if I'm sliding down, that's negative. That's how I look at it. In other words, if we were going to do the math and do final versus initial over final versus initial, we would have a negative value. In fact, y'all are familiar about what this value is. change in velocity in regard to time is the definition of acceleration. Ladies and gentlemen, boys and girls, that slope is your acceleration. And that's how I know that the ball is negatively accelerating as it's going up, because the slope is negative. It ended slower than when it started. So when I subtract 0 from a bigger number, I'm going to have a negative number. Make sense? What goes up must come down. At the tippy top, it's going to start to speed up as it comes back down right before it hits my hand. True? We're going to call this point C. And I'm literally going to cut time off, like I pause it for us to look at. All right, now let's look at this. This is Miriam. Do you have the baseball with you? So toss it up and catch it. Okay, perfect. So we start time right when it leaves her hand. So it's like play, and then we stop time. It's like a VCR or VCR. I'm dating myself. It's like having TiVo or having pausing live TV. I start right when it leaves her hand, and I pause it right before it hits her. So position, start. Okay. So let's look at this graph. When it leaves her hand, the ball is going to slow down as it goes up. It's going to get closer and closer and closer to 0 velocity as it's traveling in the positive direction. It's going to get to the tippy top. Now, guys, notice it's not staying there. It's not staying at 0. It's passing through 0. When you get to the border of a state, you don't usually stay there. You pass through. So just because the ball, this is weird, but it should make sense. Just because the ball has 0 velocity does not mean it's not accelerating. It's just passing through 0. 0 is just another number that is part of our change. Or another way to look at it is, we had positive velocity, then we had negative velocity, and when we subtract these numbers, 0 is just one of the numbers along the spectrum that we're subtracting. Negative acceleration as it was going up, slowing the ball down as it's going up, and then the same acceleration from planet Earth, changing its direction right here and speeding it up as it comes down. Okay, so far so good. Now, Miriam's going to add, let's add the hand part, okay? Let's add the hand parts. Is this, no, you're good. This is the part I erased. Okay, let's add the hand part. So now we're going to do a new graph, and we're going to add the force the ball would feel from Miriam's hand. Okay, so if we draw a free body diagram of the ball in the first example in the air, the only force that ball would feel is gravity from planet Earth pulling down on it. That's it. Again, when it's outside of my hand, I can't follow through means nothing. Remember I gave you the analogy of our coach used to yell at us when we jump up in the air? Because when we're in the air, we can't move. We have to wait till we come down and move. Next example is when Miriam has the ball in her hand. Okay? So hold it for the camera to see. What are the different forces acting on the baseball? Free body diagram of the baseball. What does the baseball feel in the Y direction? Still feels planet Earth, right? We agree? gravity from planet Earth pulling down on the mass of the ball. Why is it in the middle? Because that is the sum of all the mass, the center of gravity. I'd have to have like infinitely many small arrows, so I'm just going to draw one that adds up all the stuff and puts it in the middle. What else does the ball feel? Her hand. What direction? Up or up? A positive push or normal force. And none of us are normal, so I just like to say push. Makes a lot more sense. So the ball is feeling a push from her hand. F is equal to ma. If the ball is not accelerating, it's not speeding up or slowing down, it's staying at the same velocity, 0 is a number. That means the forces have to cancel out. That means there's no net force in either. That means when you balance your checkbook, you didn't have any change in your balance. You took in just as much as you spent. There's just as much force influencing the ball negatively as positively. Those things cancel out. The ball is not accelerating. So what would that look like on a graph? Well, if Miriam is holding the ball out for a period of time, it would look like this. A constant 0 velocity over time. And a no slope. In other words, if we calculated the acceleration, final velocity minus initial velocity over time, well, 0 minus 0 is going to be 0, regardless of the amount of time. 0. There's no acceleration. Okay. Miriam, from here, don't go down. Just literally like you'd be an elevator. Push the ball up in the air, straight up. Perfect. We practiced this all last week. It paid off tremendously. Let's describe the motion of the ball. Part of it we should know, because we just did. The part where it leaves her hand, we know what that looks like. That doesn't change. But there's this new part. When Miriam pushed the ball up, she gave that ball more force than planet Earth. Because what we're going to see when we're doing exercises is that planet Earth's not going to change what it's doing. So in order to move back and forth, you are going to have to choose to be greater or less or the same. Okay? Now, what would this part look like here? In layman's terms, the ball went from not moving to moving in the positive, right? It sped up. She sped it up. That meant it did something like this. We're going to call this point A. We're going to call this point B. We're going to call this point C. The ball sped up in the positive. A lot of different ways to look at this, but that's a positive slope climbing up the ladder. That meant that the acceleration had to be positive, which makes sense. There's more positive force on that ball than negative force. That makes sense? And because she's moving in the positive direction, the only thing a positive acceleration can do while it's moving up is to speed it up while it's going up. And if we were going to do the math on it, shake the thing. Awesome, thank you. If we were going to do the math on it, not a big deal. My final velocity is greater than my initial velocity. So when I subtract it, I'm going to get a positive number. And when I divide that by the time, it's going to be a positive acceleration. What happens next? We just did. It leaves Miriam's hand. It's going to immediately start to slow down until it reaches the tippy top, change direction, then immediately start to speed up. We did that. So in other words, when it's out of her hand, I always lose everything. Miriam, you have to help me find stuff.
Did you erase it?
Yeah. What did I do with it? The story of my life. I lose all the things.
On that side.
I wouldn't find my phone unless it rings. I just made that up. That's what I was doing. When the ball leaves Miriam's hands, guys, this is the free body diagram. That's the only force acting on the ball. Planet Earth. Her hand is no longer trying to move that ball. Even though her hand made the ball speed up, once it leaves her hand, she can't make it go faster. She can't make it go slower. She can't make it come back down any faster. If she's not touching it, she is no longer influencing it. So this should line up. The only force acting on that ball is negative. That means the ball has to be negatively accelerating. Because it was already moving up, in this case, it's slowing down while moving up. And if I said, well, if it's slowing down, that means it's accelerating. What's responsible for the acceleration? F is equal to ma. What's responsible for that negative acceleration? And you say gravity from planet Earth. That's what did it. From B to C, it was positively accelerating. So I'd say, well, what sped the ball up going up? You'd say Miriam's right hand. That's what did it. You see what F is equal to ma, how this works? Cause and effect. But these two things have to be in agreement. They have to line up. All right, the last part, Miriam, that we haven't done yet. So B, C, D, E. E, point E is where it hits your hand again. Okay, it's coming back down, and it collides with Miriam's hand. The free body diagram of that will look the same as when we had it before. More force pushing up than gravity pulling down. She slows the ball down while it's falling down. What type of acceleration must that be? Positive. What positive force must that have been from? Her hand. Guys, that's biomechanics. That's biomechanics. And all we're going to do is substitute the ball and the hand with the bar and the hands, but we're still going to see gravity there. Because it's weird, but without planet Earth pulling down on the bar, you would have to yank the bar down to you. Like you're letting gravity speed it up. You're not letting it free fall like the baseball. But it's very similar trends when we get into the exercise component. All right, let's ask a couple questions. So, do the ball toss one more time here, please. Toss it up. At the tippy top, here, is the ball accelerating? Yes, good. How is it accelerating? Positive or negative? Good. When the ball is traveling up, you may look like it's going down. The velocity is getting closer to zero, but it's still moving up. And the reason you know it's moving up is because like we're in positive land. Think of it like that. If we're above the zero, that means we're moving in the positive direction. So do not think that because the trend is going down that the ball is going down. Does that make sense? The ball only starts to go down from here on. Does that make sense?
So at the toss up,
Uh-huh.
you said it's
This would be her tossing. This is when it's in her hand and she's pushing it up. This is right when the ball leaves her hand. It's going up and slowing down. This is at its peak height, changes direction, speeds up, comes down, hits her hand again, slows down. That makes sense?
B to C is the.
Ooh, I keep forgetting we have multicolors. Thank you. Bless you. Absolutely. B to C is the amount of time it took her hand to push. And what do we know about force in time? That's impulse. And that impulse is going to change the momentum of the ball. It's going to change the velocity of the mass of the ball. It's all different ways of looking at the same thing. For your project, you may not use terms like F is equal to ma. It may behoove you to use terms like momentum and force and time, changing momentums. But I need you to see that it's all different forms of the same thing. Any questions about the baseball? Ooh. Any questions about the baseball before we do this same concept on the bench press? We're good? The key thing is that if we're talking velocity time, acceleration is part of this. It's in here because acceleration is velocity over time. No acceleration. Positive acceleration, negative acceleration, positive acceleration. No slope, positive slope, negative slope, positive slope. Climbing up, sliding down, climbing up.
Positive acceleration here.
That'd be negative.
Okay.
C to D is negative, but it has positive velocity. So again, positive acceleration, you could be traveling down. Negative acceleration, you could be traveling up. But it takes a force in a certain direction to slow you down in another direction. Think of it like this. If I threw a baseball against a wall, going maybe a horizontal analogy to understand better, and let's say the ball was traveling in the negative direction, if it was going to slow down, wouldn't it need a force in the opposite direction to slow it down? That's all we're saying. That if the ball is moving up and it's slowing down, a force in the opposite direction has to be like dragging it down to slow it down. But before it comes back down, it's got to slow down. You can't do it instantaneously. It takes time to slow down.
And A and B would just be constant.
A to B, correct. It's just, she's just holding it in her hand. Are there forces acting on it? Yes, but they're balanced. Just as much pulling down as pushing up. So no acceleration. But as soon as she starts pushing up more than the weight, it's going to start speeding up. Or as soon as she starts pushing with less than the weight, that's the part that we're going to get to the bench press. As soon as she lets off, it's going to start to speed up going down because you're going to let gravity be greater. Does that make sense?
So B to C is positive velocity with no acceleration, because that's just when it's going back her hand.
B to C is positive velocity and positive acceleration. And it's positive acceleration because the push of her hand in the positive direction is more than the weight. So it's like there's more left over positive than negative. So that's what's going to spring. That's what's going to push it up to give it velocity.
It's from D to E. It's negative, no wait.
This would be D is the tippy top. Just point D
Yes,
is the
D
tippy top.
is negative acceleration, because that's gravity.
But C to D is also negative acceleration because gravity pulling down has to slow it down. So gravity does two different things while pulling in the same direction. It slows it down, and then it speeds it up. Exactly correct. Exactly correct.
What is E F?
E to F is when it contacts your hand.
Okay.
So at point E, it hits your hand, and that positive force from the push of the hand is what's going to slow the ball down. And then if she stops it and holds it again, then we would have something like this again.
C to E is negative acceleration with positive velocity. D to E is when they're both negative.
C to D is negative acceleration, positive velocity. D to E is still negative acceleration, but negative velocity. These E's, they sound a lot. Just want to make sure, abduction and adduction. Okay. All right, we're good. Let's do our next scenario. Our next scenario, I think we're going to save the bench press for Friday because I think this is going to help us transition better. Let's say Miriam, let's go back to the baseball. And what Miriam is going to do is she is going to lower, it's never going to leave your hand. She's going to lower it down, change the direction, and bring it back up. Just nice and slow, never leaves her hand, down and up. Think of it like an elevator. Here's the low person on the elevator. It's not moving. It has to speed up, but it's not going to keep speeding up. It's going to hit a constant velocity, slow it down, and now bring it up. Okay? So let's do the baseball in the hand like we would an elevator. What would happen in the elevator? Speed up, constant, put on the brakes, stop. Speed up, constant, stop. Okay? Let's look at what that would look like. If I can find mine, please. It's this part, right? Okay. I'm so silly. Okay, baseball is in the palm of her hand. Constant zero velocity, no acceleration. Free body diagram, hand and gravity, right? And they are equal. Push from the hand. These two cancel out. Guys, that's like I made $100, I spent $100. My balance in my checking account stays the same. It didn't accelerate. Okay. This is the part that we're working towards. This is the magic of weights and exercise. When Miriam starts to go down, if planet Earth stopped pulling on this ball, this is what would happen. Does that make sense? So it's not her hand that sped the ball up, even though she's pulling it away from it. You still need planet Earth to be pulling down to negatively accelerate the ball. So what it's going to look like is when the ball speeds up going down, she's not pushing on it as much. She's pulling away. She's pulling off. She's letting planet Earth be the greater external force. Thus, a negative force is going to cause a negative acceleration. Now, it's not going to be a lot. It's only going to be a little. But it's going to speed up. The ball is going to speed up in the negative direction in that scenario. True? In other words, it went from not moving to moving down. It had to speed up in the negative direction. What was my acceleration? Negative. It doesn't mean I wasn't a positive force on it. It just means that planet Earth was greater. Now, the constant speed, she's letting it go down at a constant speed. Let's say it's 2 miles an hour. A constant 2 miles an hour. Let's say this is negative 2 miles per hour. I stay at 2 miles an hour. Point A, point B, point C. What was my acceleration from B to C as I had a constant negative velocity? What was my acceleration? I didn't have an acceleration. Stayed the same speed. And this is the magic of what I was trying to tell you guys last week. In order for that to happen, planet Earth can't keep being greater than my hand. If planet Earth kept being greater, the ball would keep speeding up. If my hand pushed more, the ball would start to slow down. The only way to keep the speed going the same is to tie. Is for Miriam's hand to push back on the ball with the exact same force, just in the opposite direction. So when you're doing that bench press, and it's 135 pounds, and you let it speed up, you're doing less than 135 pounds of work, of force. But to maintain that speed going down, you're no longer doing less than 135 pounds of work. You have to be doing 135 again. Because if you push less, it would keep speeding up. And if you push more, it will start slowing down. The only way to keep a constant speed is for the forces to be balanced. What speeds up must slow down. So Miriam with the baseball, or in the case of the bench press, she starts to slow it down, the elevator. That means she's going to push with more force than the weight. We're going to slow it down while it's still going down. Positive acceleration. That makes sense. She's got to push up on it more than the weight. Guys, this trend right here is 1/2 of the bench press. Start, finish. Planet Earth sped you up. You kept it going at the same speed by time, and then you have to be greater to slow it down. And if we were going to come back up, it would look like this. Speed up going up. Heck, you know at the bottom, you got to speed up coming up. That's the hard part. This is the hard part. This is where your muscles have to be greater than the weight to slow it down going down and to speed it up coming up. This is when you're really working. This is when you're actually doing more than that ball or that weight, or the weight of the ball or the weight of the plate. Speed it up. Ideally, you'd love to have a constant velocity, and then you're actually going to let off. And you know you do. At the top, you're like, ah. It's easier right at the end because you let off to let gravity slow you down. Where are we at on time? Oh, I got time. Negative acceleration, because gravity is going to be greater than your hands. Planet Earth is speeding you up. Constant negative velocity, no acceleration. That means these have to be equal. They have to tie. Slowing down as I'm still going down. Slowing down while I'm still going down requires a positive acceleration. I have to push on that ball or on that barbell more than the weight. And guys, you know this, you feel this. Anytime you're doing an exercise, in the squat, is it easy to start? Heck yeah. Is it easy to change the direction at the bottom? Heck yeah. Because that's when your muscles have to be greater than the weight. Slowing yourself down as you're falling down requires a positive acceleration greater than the weight you're trying to do. And don't forget, it's not just a barbell you're squatting, it's your body weight too. I didn't mean to sound like Dr. Seuss right there, but that matters. Negative acceleration, speeding up, going down. Zero acceleration, constant speed of going down, positive acceleration, slowing down, going down, positive acceleration, speeding up, going up, constant velocity, going up, negative acceleration, slowing down, going up. That is a full range of motion in the bench press. Just like we did a full range of motion if we would let the ball go down and make the ball go up. Miriam, if you don't want to do the ball again, okay, start at the beginning, slowly go down, change the direction and come back up. Sorry, slowly go down, change the direction and then slowly go up. A to B. A to B is when it starts to speed up. B to C is when it's constantly going down, the same speed. C to D is when it's slowing down, going down. D to E is when it's speeding up, going up. E to F is constantly going up. And then F to G is when it's slowing down, going up. The reason velocity time graphs are the best, because it tells us the acceleration in there, because acceleration is velocity over time. It tells us the position, because if the point is above zero, I'm moving up. And if it's below zero, I'm moving down. And the trend to zero is either speeding up or slowing down. If I'm getting further away from zero, I'm speeding up. If I'm getting closer to zero, I'm slowing down. It tells you all of the kinematics. It tells you all of the linear kinematics. And it also tells you all of the kinetics. Because in order to speed up or slow down, there has to be some force to it. And if we know the scenario, like the bench press or the ball, then we know those forces. Application. The barbell weighs 135 pounds. We don't use meters per second in this class. We don't use newtons in this class because we live in America. And in America, we know miles per hour, right? That's what we know. Did you hear so-and-so broke the world record, jump 1 point something meters? I don't know what that means. Okay? So, 135 pounds on the bench press. Where's the ball? This is an analogy. Miriam's hands, as she's holding that bar out, is feeling 135 pounds. The ball has to be feeling the exact same amount of push. Thank you. But I just want to show them that we're using the same analogy. The bar has to be feeling the same amount of positive push as that it's feeling in the negative for it to not be accelerated. The trick here is when you start to bring it down, it's not that you yank it down, it's that you push less. And by pushing less than 135, now planet Earth is like, ooh, I'm greater now. I can accelerate the bar negatively. Planet Earth can speed it up going down. It's not a free fall. You're not just going to pull your hands away. But once you hit a speed, a negative speed that you want, in order to keep it going that same speed, you no longer are pushing less than the weight. That's important for biomechanics to understand. In order to keep that 135 going down at the same speed, you're doing 135 pounds of work. My freshman year of college, I had a professor, I'm not gonna say who it is, but you know, say concentric happens when you're working more than the weight, and eccentric happens when you're working less than the weight. And what I learned is, you're good. Concentric happens here when you're working more than the weight, but concentric also happens here when you're working less than the weight. And concentric also happens here when you're working the same as the weight. That's important for us to understand. That's important for us to understand. Boom. All right, we're gonna play more on Friday.
Oh, next Wednesday, there's gonna be,
Sure.
they're gonna get training in the parking lot. They're be doing the softball day for softball. I don't know how many parking spots are gonna be taken away, so they're gonna start